Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to continue talking about series and seeing how series converge and trying to figure out when series converge. And we're going to talk about something specifically called the integral test. This section and next several sections after it, we're going to be focusing on different tests or different methods to figure out if a series converges. So let's just recap for a moment. We learned about the sequence of numbers, we called them a sequence, and we talked about the convergence of that sequence of numbers. Just trying to figure out what the elements of the sequence do and how they march off, if they march off towards a limit or not, okay? And then we talked about a series and introducing that, and we said that that was just adding up an infinite number, if it's an infinite series, which is almost always the case, adding up an infinite number of numbers in a sequence. Okay, and so what we're doing is, we're trying to figure out in this section and the subsequent sections, let's define several tests that we can put in our tool bag and look at a series on a test, and they say, look at this series, does this series converge or not? Okay, in other words, the infinite sum here that you're doing, does it add up to a number? Does it converge? Or does it just blow up and go to infinity and doesn't converge at all? So the next several sections are going to deal with that. Now recall, and I think I talked about this in the last section, recall that when you look at a sequence, or if you want to think about it, a series is a sum of these sequence of numbers, okay? The sequence itself, if you were to plot it on a graph, at n is equal to 1, 2, 3, 4, 5, you're just going to have points there. So you're going to have a value at n is equal to 1, a value at n is equal to 2, a value at n is equal to 3. I mean, these are the values, the elements of the sequence, if you will, okay? So you could plot it, and there would be little dots on a graph that would correspond to whatever number n you're talking about, the element in the sequence, okay? And we also said that the series is when we add all of those numbers up, the elements of the sequence, okay? Now, we made the analogy in the last section that a sequence, when you plot it like this, and little dots on the graph, it looks kind of like a function. The form a sub n, giving you the elements of the sequence, or the terms in the series equivalently, right? It looks like a function. It's not a function, okay? It's not, because a function is a smooth, continuous thing that you can graph and have infinite number of points all over the place, okay? Whereas this series thing is adding up discrete points spaced an equal distance apart there at every value of n, okay? But still, to the naked eye, you look at the graph of a sequence or a series of the points that are defined at every value of n, and you see patterns and trends, and you can kind of imagine that it was a smooth function there, okay? So what I'm getting at here by telling you all of this is that we can use our knowledge of functions and the calculus of functions to apply to the convergence of a series. They're not the same thing. They're not the same thing at all. But by analogy, you can use some of the things in your tool bag that you've learned from functions. Okay, so the first thing we're going to look at is the integral test. Okay, so just big picture, totally big picture. Remember what an integral is. Okay, when you go back to the definition of the integral way back in Calculus 1, you'll see that the integral is a summation. It's a summation of an infinite number of things that we have reduced down to 0. That's what the dx is in the integral. It's differential x. It's an infinitesimal part of x, dx, and whatever you're integrating there in the integrand is just something that you're summing over. You're summing those it's not a term, you're summing that function really over differential values of x, and you're adding them up. And that's why an integral is equal to the area under the curve, because you're chopping that guy up and you're adding them up over infinitesimal amounts of dx, and you're adding the whole thing up, okay? So by comparison, when we're trying to find if a series, not a function, but a series converges, remember a series is also a summation. It's a summation of infinite number of points, okay? So the two have parallels. The integral is an infinite sum of the area under a continuous curve, okay, which is a sum of little slices of a function there, okay? And this series thing, we're just adding up points. So they're not the same, but they all involve adding up things, an infinite number of things, okay? So smart people way before us invented this thing called the integral test, okay? What we're going to do is we're going to use improper integrals to test the convergence of an infinite series, and we're going to do it like this. Let me just go ahead and write the integral test down, and it's really simple actually, and then once we do that, we will be able to tackle some problems. Okay, so we're going to talk about the integral test. And I should say the integral test for series convergence. That's what it is, and I'll just even write it that way. For series convergence. And I'm going to put CONV, convergence there. So we have a test here. We're going to put it in our tool bag. We're going to pull it out. And we're going to use it when it's useful to figure out if a series converges. Let me say one more thing before we get started. We're not going to calculate the value of the series. We're not going to calculate the actual sum of the series. That would be the number that all of those things add up to equal, okay? We're just going to apply a test to obtain the knowledge if the series converges or not, okay? That's all it tells us. It doesn't tell us if it adds up to 10 or 49 or 3. It tells us if it converges or not. And actually finding out what it converges to is usually very difficult and not even really something you study all that much in calculus because it's very difficult. All of these tests that we're going to study here in the next few sections are going to be telling you if the series converges or not. Okay, so this is what you do. The first thing you do is you form, there's a lot of words here, but it's really not that bad. Form a continuous function FUNC is function, f of x from the terms of the series a sub n. Okay, so we have elements of a series that we're adding up, and we're going to form a continuous function. So we're going to pretend, for lack of a better word, that these discrete points that form the series that we're adding together here, n is equal to 1, 2, 3, 4, 5, and 6. For lack of a better word, we're going to pretend that these guys actually form a smooth function. That's all that means. Okay, so you don't actually have to do much work there to form a continuous function. All it says is really you could replace that sentence with pretend that the elements in your series are actually a smooth continuous function. That's really what it means. Okay. And then we're going to assume that f of x is positive and decreasing. Okay, assume that f of x is positive and decreasing, and I'll say one word about that. Remember, in order for this series to have a hope and a prayer of actually converging, the terms or the elements of that series that you're adding up must decrease to 0. It doesn't mean that it will converge, it just means that you have a hope and a shot at it. If those terms do not decrease, if those terms get bigger and bigger as n gets bigger, there's no way in any way, shape, or form that they're going to add up to anything less than infinity. Okay, so we're assuming that f of x is positive and decreasing because otherwise the series is known to diverge already. Okay, so you have to be in that boat. Okay, so then we're going to have a part A, and part A says, so we're going to assume all this stuff, which really is no work on your part. It just says, okay, assume this is the case. Then we're going to say, if the integral from 1 to infinity of f of x dx converges, comma, then the sum from n is equal to 1 to infinity of a sub n, which is the series that we were interested in testing in the first place, converges. Okay? And we'll talk about it in a second. Part B, I think you could probably guess what it says. If the integral from 1 to infinity of f of x dx diverges, comma, then the sum from n is equal to 1 to infinity of a sub n diverges. The series diverges. Okay, that is it, ladies and gentlemen. This is the integral test. It's called the integral test of series convergence, and you're going to have to learn this because this is one of those things you're going to have to remember on your test and apply. Okay, so let me draw a little break here to kind of separate the math there. What is this saying? Okay, all right, we have a series. It consists of elements a sub n that we're adding together. And we're pretending that these a sub n's form a continuous smooth function even though they really don't. And the reason we assume that is because integrals only operate on functions. Somebody a long time ago proved that if you make this assumption, you can operate on it with integrals and you're okay. That's not for us to prove, that's just something that we're going to remember and use, okay? So what it's saying is, remember, we're trying to find out if this series converges. That means, does this series add up to a number, okay, or not. If it doesn't add up to a definite number, if it goes to infinity, we say it diverges, okay? If it adds up to a number like 2 or 3 or 0 or whatever, then we say that it does converge, okay? So by analogy, what we're saying as before is that these sets of elements that we're adding together, okay, somewhat behave like a function, and if we take the integral of that equivalent function from the same limits, 1 to infinity, that we were adding up to begin with. So it's still an infinite sum because an integral is a sum. It's just a sum over a continuous function, okay? If this integral converges, in other words, if this integral, if you get an answer that equals a number and not infinity, then you have proven that the series also converges. And if the integral diverges, if you actually get infinity here when you evaluate this integral, then it says that the series diverges. It has no information at all about what the series actually converges to. The answer that you get out of this integral, let's say you evaluate that integral and you get 5, okay? That has nothing to do with what that series actually converges to, because this integral is an integral over a continuous function, and so you're adding up what's under that continuous function. That has nothing to do with this. It's just simply saying that by analogy and by the proof, long mathematical proof that I'm not presenting here, that if this converges, then that also means that the sum of these terms converge, but it has nothing to do with what this actually adds up to, okay? So it's a little bit of a leap of faith, but it kind of makes sense because an integral is a sum, and obviously this sum is a sum, and so by using integrals, we can get the answer. And so you know lots of techniques of integration now. You know about L'Hopital's rule, you know about trig substitution, you know all kinds of crazy things and ways in which to evaluate integrals. So almost all of the problems in this section, in fact all the problems in this section, are going to boil down to integrating stuff. And you're going to get the answers and you're going to be able to tell if those series converge or not. Okay, so we're going to go off and do some problems, but before we do that, I want to introduce you to another very important series that you're going to have to commit to memory. We've already talked about the geometric series in the last section, so that one's one you have to commit to memory. Now we're going to talk briefly about the p-series. It's not something you want to skip. You need to understand the p-series because you're going to see as we go on, you're going to be using it a lot to prove the convergence of series. Okay, so we're going to talk about something called the p-series. You'll see why we call it that in a second. It's pretty simple. But the p-series looks like this. The sum from n is equal to 1 to infinity of 1 over n raised to the power of p. Now I think you see why it's called a p-series. P is a number, okay? In fact, I'm going to write that down to make it explicit. Okay, p is just a number. So it could be 1 or 2 or 3 or -1 or whatever, okay? Now, what is proven in the books, and what sort of makes sense, but it's not something we're going to prove here with any sort of rigor, this series converges if p is greater than 1, and it diverges if p is less than or equal to 1. Now, entertain me for a moment here. You know that this is 1 over n to the p. So this is the same n as this. So the terms in this series are getting bigger, the n's are getting bigger and bigger. So it's 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, and you're adding all of these up, okay? So if you pick a p, let's say this is squared. Let's say it's 1 over n squared. Those are the elements. That's a p-series, okay? So you need to be able to recognize that. So that would mean as the numbers increase in n, the terms are getting smaller and smaller and smaller and smaller. Okay, and for the p-series, you can see right away that the terms in the p-series are going to decrease towards 0. As n increases, the denominator gets bigger and bigger and bigger, so the terms are getting smaller and smaller and smaller. But the magnitude that they get closer and closer to 0 is totally dependent on p. If p is equal to 100, let's say, then you're going to have terms 1 over n to the 100th power, and they're going to approach 0 incredibly fast. Okay, and so the faster the terms approach 0, the better chance you have at the thing converging, because you know they need to approach 0. They have to approach 0 in order for this thing to have a hope and a prayer of converging. But the faster they approach 0, the more likelihood there is going to be that it does converge. So what the theorem says is that if p is greater than 1, these terms are approaching 0 fast enough so that that series converges. If p is greater than 1. So 1 over n squared, 1 over n to the 5th, 1 over n to the 100th. Those terms are approaching 0 fast enough so that this thing converges. If p is less than or equal to 1, the terms are still approaching 0, but they're not approaching 0 fast enough for this thing to converge. So the terms still approach 0, but they may be approaching 0 very gradually, and so you never actually converge. Whereas if p is greater than 1, the terms are approaching 0 very rapidly, and so the series does converge. So keep that in mind. You do need to know this one because it is going to be something you use. Okay, let's go ahead and work some problems. The first problem is going to be, and in all of these problems, what we want to do is find out, does the series converge or not? That's our question in life. The sum from n is equal to 1 to infinity of 2 over cubed root of n. That is our series. Those are the terms that we're adding up. We have an infinite series, obviously. We want to see if this converges. Now, there's one thing I want to teach you, and I kind of waited till I had an example here. I want to show you something that's kind of important here. This is a little useful rule that you're going to need to know. This is a little theorem. It's a super small theorem, but you need to remember it. Okay? And I'm going to write it down like you'll see it in a textbook and show you a practical example. The sum from n is equal to 1 to infinity of c times a sub n, so it's just a constant, some number c times the elements in the series, is equal to c times the integral from n is equal to 1 to infinity of a sub n. All this is saying is that if you have a series and you're adding up these things and it's an infinite series and you have a number c, okay, times the elements of the series, then you can pull that c out of the summation sign and put it on the outside. It's exactly the same thing as an integral. And an integral, you can pull out a constant, and you always know this, you learned this in calculus, okay? And the reason that you can do it for both cases is because an integral really is an infinite sum when you go back and look at the definition. So you can pull out constants from your sums. The reason I bring it up is because look at this one, you have a 2 on the top. So I can rewrite this as 2 times the summation from n is equal to 1 to infinity of 1 over square root of cubed root of n. Cubed root of n. I can write it like that. That's perfectly legal. Sometimes it's useful. Okay, now let's continue simplifying and see how far we can get with this. 2 times the sum from n is equal to 1 to infinity. Okay, this is going to be 1 over n to the 1/3 power. Okay, because this is a cubed root, and I can continue this and say this is 2 times the sum from n is equal to 1 to infinity of 1 over n all to the 1/3 power, because I have 1 on the top and into the 1/3 on the bottom, so I can wrap it up like this. If I apply the 1/3 to the top, I'll get this, and if I apply the power 1/3 to the bottom, I get that. So that is perfectly valid. Now compare that, this guy here, to this p series that we just looked at. That is a p series, okay? You can look at this version if it makes more sense to you. 1 over n to the 1/3, 1 over n to the p power. Okay, 1 over n to the p power. Now in this case, we know that this is a p series. So this is what I would write on my paper, p series. Okay, and I would put p is equal to 1/3. And since p is less than or equal to 1, this diverges. Okay, so you see why I say that it's important to understand the different series, especially the p series and the geometric series, because if you can beat the series that you have into the form of one of those, and you know how those things converge, then you can get the right answer. Okay, so in this case, it didn't really look like a p series, but we pulled this out, we changed this into a fraction, and it looked like it was 1 over n to the p, and p was less than 1, and so we knew in that case that it diverges. So my advice to you is anytime you get something with a fractional or some kind of exponent like this, try to see if you can beat it into the form of a p series or a geometric series first. That's probably one of the first things I would do. Okay, the next problem is going to be the sum from n is equal to 5 to infinity of 1 over n to the 1.0001. That is my series. And we're going to be using the p series quite a bit in this section, so I'm going to write that down over here. The p series, for reference, is basically when the sum from n is equal to 1 to infinity of 1 over n to the p, okay? And it converges for p greater than 1, and it diverges for p less than or equal to 1. That's important, so I'm going to keep it up there, for this section. Okay? All right, so what do we have here? It looks like we have a p-series, 1 over n to a power, okay? But the only thing is, and you'd be tempted just to say that it's equal, but the only difference here is that, look, n starts from 5 to infinity. It doesn't start from 1 to infinity, so you're not really quite sure. Does it apply? Does it make sense? Is it exactly valid to say this? Okay, well, you can say that if it were a p-series, if it were governed by this, since p is greater than 1, this thing's going to diverge. That's something, I'm sorry, it's going to converge. That's what it's going to do. You can see that by inspection because it's greater than 1. Okay, the question is, does it matter if you start from 5? Okay, let me do a little thought experiment with you. Okay, what you're doing is an infinite sum of things. What you're trying to do is find out if that infinite sum converges to a number or not. Okay, the fact that this one starts at 1, it starts at 5 rather than starting at 1, okay? It doesn't really matter, is the short answer of it, okay? It matters if you were trying to actually calculate the sum of the series. Obviously, the sum of the series when you start from n is equal to 5 is going to be different than if you had started from n is equal to 1. So the sum, the actual number that you're adding up and actually arrive at is different in those cases. But to actually see if it converges or not, it really doesn't matter. Because if it did start at 1, let's say it did start at 1, to infinity, then you would have several extra terms here at the beginning. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. You would have those 4 terms at the beginning of the sum, but then you would be continuing on with n is equal to 5, 6, 7, 8, 9, and so on and so on. So the first 4 terms that you're adding to the front are just going to end up being an additive constant. They're a fixed number, okay? And whether or not the thing converges or not is not going to depend on the first 4 terms. It's going to depend on how the thing approaches as you go off to infinity. So for practical purposes, to boil it all down, yes, you need to be cognizant when it says something other than n is equal to 1 down here when you're doing your comparison to the series. And yes, it would definitely impact the actual sum you would get if it started at 1 or started at 5. But when you're talking about convergence, whether it converges or not, starting at 1 or 2 or 5 doesn't really matter. It's the behavior as you approach infinity that's going to dominate everything, okay? So you can rationalize it that way, and then you could say that since p is greater than 1, and this is a p-series, then it converges. The series converges, okay? All right, let's go on and do the next problem. Let's say you have the sum from n is equal to 5, again, to infinity, of 1 over n minus 4 squared. So these are the elements of a series that I'm adding up, 1 over n minus 4 squared. I'm starting at n is equal to 5, okay? But I'm going up to infinity, and I'm trying to figure out if this thing converges or not. So it doesn't really look like a p-series, okay? This certainly doesn't really look like a p-series. It doesn't look like 1 over n to the p. You have this minus 4 in here. It doesn't really look like a geometric series either if you go back to what the geometric series looks like. Okay, so you might think, well, I can't use either of those. Well, we can go ahead and use our integral test that we talked about. Okay, we can do that. So what we're going to do to find out if this thing converges is we're going to pretend that this is an actual integral, right? And we're going to say, okay, well, what is the integral from 5 to infinity of 1 over x minus 4 squared dx? That would be the equivalent integral. The theorem says, pretend the elements form a function, so we just replace n with x, and integrate this sucker there. Now, if you look back, you'll see that the integral test talks about going from 1 to infinity. And this series starts at 5 to infinity. Well, the same rationale as before. It wouldn't matter if you were trying to calculate the actual sum, but when you're actually just trying to check for convergence or not, the lower limit right here really doesn't matter. Doing an integral from 5 to infinity, if it converges, tells you the same information than if you had started from 1 to infinity, because that difference between 1 and 5 is just a constant. So it's really not going to, that part's not going to make it diverge or not. It's the behavior as you approach infinity that's going to matter. So if you see something like this and you're trying to wonder if you can apply the integral test because it doesn't start from n is equal to 1, the answer is you can use the integral test from some arbitrary number, but it does have to go off to infinity. So let us solve this integral and see if it converges or not. Well, this is going to be solved by substitution, and we're going to say u is equal to x minus 4, which is the bottom here. And we're going to do that because we want a polynomial down there. It's easy to integrate. So we'll say du dx is equal to 1, integral of the right-hand side, and so then du is equal to dx. Okay? So let's go ahead and plug it in. Continuing on over here, you'll have integral from 5 to infinity, 1 over u squared, because u is equal to x minus 4, times dx, but we said dx was equal to du. Okay, so look, you have a nice simple integral here. I always like to write these integrals when I have 1 over something raised to a power as a negative exponent, because it just helps me when I apply my exponent rule. 1 over u squared is equal to u to the negative 2 power. Okay, so this is going to be equal to 1 over exponent plus 1, which is negative 1, times u to the exponent plus 1, evaluated from 5 to infinity. Okay, now obviously my limits here are in terms of x and not in terms of u, so I'm going to need to plug in here. So what I'm going to have is negative 1 over u evaluated from 5 to infinity, just pulling this downstairs and keeping the negative sign. And obviously u was equal to x minus 4, so it's negative x minus 4 on the bottom, evaluated from 5 to infinity. Okay? Evaluated from 5 to infinity. So what would this be if I were going to evaluate this guy here? I would say, well, I'm going to evaluate over at infinity. I've got negative 1 over, what is infinity minus 4? Let me ask you that. What's infinity minus 4? It's still going to be infinity, so I'm going to put that down there. Minus, because I'm going to evaluate down here, minus, don't forget I have a negative, so it's minus a negative 1 over, plugging in 5 minus 4. So it's 5 minus 4 over here. Right? Just make sure and keep track of your negatives. This becomes from the theorem of calculus, that you evaluate the upper limit minus the lower limit, and this negative just is because the thing we're evaluating is negative. So what I'm going to have is negative 1 over infinity plus 1 over 1, which is 1. Okay, so this is going to be 0, 0 plus 1, which is 1. So the thing converges to 1. So what does that tell you? The integral, the corresponding integral that corresponds to the series did converge. So that means that by definition, the series converges. This number, 1, has nothing to do with what the series converges to. It doesn't tell us that the series actually adds up to 1. It just says that by looking at the corresponding integral and that integral converging, the series converges. That's all it tells us. Okay? So we're going to move on and do a different problem. We're going to say, what if you have the sum from n is equal to 1 to of 1 over square root of n plus 1, okay? And you look at this first and you say, well, let me see if I can find this and make this into a geometric series. Let me see if I can look at this and make it a p-series. Neither one seems to work, so let's go ahead and apply the integral test. Well, I can go ahead and rewrite this as n is equal to 1 to infinity, 1 over n to the 1/2 plus 1. I just like to have those in terms of exponents. And if I'm going to apply the integral test, I can integrate from 1 to infinity, 1 over x to the 1/2 plus 1 dx. Okay? X to the 1/2 plus 1 dx. Okay? So let's go ahead and try to see if we can integrate this thing. Let's do a substitution. Let's go ahead and try. I mean, substitution is always going to involve trying different things and trying trial and error. So let's go ahead and try to set the denominator equal to u. U is equal to x to the 1/2 plus 1. Okay? So then du would be equal to 1/2 x to the negative 1/2, and derivative of 1 is 0. So its exponent comes down, x to the exponent minus 1. Okay, and this is du dx, okay? So then what I'm going to have here is dx is going to equal, moving dx over here and taking this and pulling it over here, 1 over 1/2 x to the negative 1/2 du. All I did was take dx and move it over here and take this entire thing and divide it over here. I'm doing things one step at a time. So then dx would be equal to taking the 2 and flipping it up, 2, and moving the x to the negative 1/2, it would be like this. Taking everything and moving it upstairs. 2x to the 1/2 du. So let's go ahead and try the substitution. Integral from 1 to infinity of 1 over u times dx, but dx is 2x to the 1/2 du. Well, you might look at this and say I'm stuck because I did my substitution. I ended up with x to the 1/2 here, and there's nothing to cancel it with. But look here, the thing that the definition of u is x to the 1/2 plus 1. So if I were to take this, okay, and solve for x to the 1/2, x to the 1/2 with my self-consistent definition of u is equal to u minus 1. So I can take this and plug it in here. That's perfectly legal to do. 1 over u times 2 times x to the 1/2, but I can say that that's u minus 1 du. That's perfectly legal to do. You substitute your u in and you hope everything cancels, but if it doesn't, if you can back substitute in for what you know x is equal to and get everything in terms of u, that's perfectly legal. Okay? So this is going to be equal to the integral from 1 to infinity. It's going to be equal to 2 times the integral from 1 to infinity. And what I'm going to have is u minus 1 over u. And so I'm going to write that as u over u minus 1 over u du. Make sure you understand that. All I did was you have u minus 1 over u. So the first term, I can break the fraction up and I can say it's u over u minus 1 over u. And if you're not quite convinced of that, go ahead and add these fractions back up. U minus 1 on the top, u on the bottom, because I have a common denominator. And why did I do that? Because I'm continuing to simplify. 1 to infinity, u over u is 1 minus 1 over u du. Now I think you see why I did it, because that integral is pretty easy to evaluate. Integrating this, integral of 1 is u plus integral of, actually it's minus integral of 1 over u is natural log of u, okay, evaluated from 1 to infinity. Evaluated from 1 to infinity. Now I have two choices here. My limits of integration are in terms of x, but my integral itself is in terms of u. So usually when I get to this point, I back substitute what I know for u and put it in here, and I'll substitute x to the 1/2 plus 1 here, and I would evaluate everything. But that's going to be kind of an ugly expression inside of here, and I just don't want to do that. I want to do something a little different for you this time to broaden your horizons a little bit. So another way to do that is, rather than plugging in what you know for u is here, you can convert the limits to integration to u, okay? Notice that u is equal to x to the 1/2 plus 1. These limits of integration are in terms of x, okay? So I could write over here that then u would equal infinity to the 1/2, because this is x, so I'm plugging into x to the 1/2 plus 1, and that's obviously equal to infinity. And this would mean that u is equal to plugging in 1 for x, 1 to the 1/2 plus 1, which is equal to 2, because square root of 1 is 1 plus 1 is 2. So basically, instead of plugging in here and then evaluating in terms of x, I'm just going to change the limits of integration, but I'm changing it according to my own definition of u, so everything's self-consistent. So the new limits of integration are from 2 to infinity. That's the bottom line, okay? So if you were going to evaluate that, you'd say, okay, evaluating at infinity, I have u minus natural log of infinity minus, evaluating at 2 minus natural log of 2. Okay, and actually, what I meant to write here was infinity minus natural log of infinity, because I'm plugging in here. 2 minus natural log of 2. Now what is this? Infinity minus natural log infinity. Well, that's still big fat infinity, right? Because this is infinity here, this is infinity here. You subtract them, you're still going to get some infinity, right? Minus 2 minus natural log of 2. Well, at this point I can kind of stop, because I have infinity, which is an incredibly large number. It's infinite minus some finite number. This is just a number. So this integral is equal to infinity. So this integral diverges. So because the integral diverges, the series diverges. And it diverges because this integral does not converge to a number. It diverges because this integral does not converge to a number. And one thing I want to point out to you here is that when I went from this step to this step, I just evaluated the integral here, right, which is this. Never forget that I still have this 2 out front, okay? And so that means that when I evaluated the integral here, I still had this 2 out front, but it didn't really change anything because, you know, I had infinity on the inside times 2 still gives me infinity, okay? So when you're doing this stuff and you're evaluating your integrals, never forget that if you have numbers that are sitting outside of the integral like that, those are going to matter too. In this case, it didn't matter at all because it diverged to infinity, so the series diverges as well. Okay, now the next problem is, what if I have this series, n is equal to 1 to infinity, of n e to the negative n squared. Okay, those are the terms, n e to the negative n squared. So it doesn't look like a p-series or a geometric series, so I'm going to evaluate the corresponding integral. I'm going to evaluate from 1 to infinity of x e to the negative x squared dx. Okay, so I just need to evaluate that integral and see if I can get that thing to converge or not. So notice I have an x squared here and I have an x out front. So if I choose u to be x squared, okay, then I'm going to take the derivative and get x, or 2x I should say, which is going to cancel with this x here. So what I'm going to do is I'm going to say u is equal to negative x squared, du dx is equal to negative 2x. So then dx, which is what I'm going to need to plug in here, is equal to 1 over negative 2x du. That's what I need. Okay, so let's go ahead and plug that in. And what we will see is that's equal to the integral from 1 to infinity of x times e to the u, because u is negative x squared, times dx, which is defined as negative 1 over 2x du. And you can see right away that the x cancels with the x, so that's good. And what I'm going to do in the next step is I'm going to take the negative 1/2 and pull it out of the integral. So negative 1/2 times the integral from 1 to infinity of e to the u du, and you should know right away that the integral of e to the u, or e to the x, whatever, is equal to e to the u. It's an indestructible function. So it's 1/2 e to the u evaluated from, don't forget I got the 1/2 here, it's equal to negative 1/2 times e to the u, which is the integral of this, evaluated from 1 to infinity. And what I'm going to do to go ahead and evaluate the limits is I'm going to plug in what I know for u. And then I'm going to evaluate the limits of integration. Negative 1/2 e to the negative x squared evaluated from 1 to infinity. Negative 1/2 e to the negative x squared from 1 to infinity. Let's go ahead and evaluate that. Okay, what I'm going to have here is I'm going to have the first term is negative 1/2 times e to the negative x squared, so it's negative infinity, because infinity squared is infinity, okay, minus a negative 1/2, because it's negative, so minus a negative 1/2, e to the negative 1 squared is 1. So I have e to the negative 1 right there, okay? I have e to the negative 1 right there. So what does this reduce to, okay? So I've got negative 1/2 times, what is e to the negative infinity? Well, that's the same thing as 1 over e to the infinity, right? So it's going to be 0 because that denominator is going to go through the roof. So I'm going to be dividing by 1 over infinity. So this is 0 right here, plus, because of the double negative here, 1 over 2e. So the answer here is 1 over 2e because I've multiplied by 0 here, okay? So the integral converges. So we had a series, we found the corresponding integral, we integrated that guy, we did our substitution, and we found out that the integral converges. So because the integral converges, the series converges. Okay? Moving along, what if you had the sum from n is equal to 1 to infinity of n over n squared plus 1? That's my series. Okay. Again, doesn't look like a p-series, doesn't look like a geometric series, so we're going to use our trusty integral test, and we're going to say, okay, well, I'm going to integrate from 1 to infinity x over x squared plus 1 dx. Now look, we have an x on the top and we have a term in x squared on the bottom. So if I take u to be x squared plus 1, if I take the derivative of that, I'm going to get 2x, and that x is going to cancel with that one. So it looks like a nice cancellation is in order. So I'm going to say u is equal to x squared plus 1, du dx is 2x, okay? And then dx is equal to 1 over 2x du, and I'm going to need the dx here, and that's why I solved for it. So what I'm going to have is integral from 1 to infinity of x over u, because the whole bottom x squared plus 1 is equal to u, times dx, but dx I just found as 1/2, or I should say 1 over 2x du. And I see right away that I'm getting what I like. This x cancels with this x, and so this is going to equal, pulling out the 1/2 integral from 1 to infinity of 1 over u du. And you should know right away that the integral of 1 over u is a natural log. So that's 1/2 times natural log of u evaluated from 1 to infinity. But we don't actually want to evaluate it yet because I have my answer in terms of u and my limits in terms of the other thing there in terms of that. So what I'm going to do next is I'm going to say 1/2 natural log, and I'm going to plug in what I know for the natural log, I'm sorry, for the u, which is x squared plus 1, evaluated from 1 to infinity. And let's go ahead and do that. It's 1/2 times natural log of infinity, plugging in infinity here, infinity squared plus 1 is infinity, okay, minus 1/2 natural log of 1 squared plus 1 is 2, okay? Now, what do you think we have here? We have 1/2 times natural log infinity. Natural log infinity is going to be infinity. If you put that in your calculator or draw a graph, you'd see that. This, whatever it is just going to be a number, so you have infinity minus a number. So the answer is infinity. So the series, because the integral did not converge, the series diverges. The series diverges. Okay, we have a couple of more problems to continue getting some practice with the integral test. N is equal to 2 on up to infinity, 1 over n times natural log of n. Okay, those are the terms of my series. That looks nothing like a geometric series or a p-series. And I'm going from n is equal to 2 to infinity, but we said before that when we're using the integral test, the lower limit doesn't have to be at 1. You can still take the integral of the equivalent function, okay, over dx, and if that integral converges, then the series converges, okay? So let's do that. Now, what type of substitution would you use here? You have x times natural log of x. You want to be able to cancel something here if you can. Think about this. If you took u to be natural log of x, what is the derivative of natural log? It's going to be 1 over x. So there's a chance that that 1 over x might cancel with this x. The only way you're going to know is by actually trying it, so let's go ahead and try it. If we said u is equal to natural log of x, then du dx would be what? 1 over x. So because we need dx, we'd say dx is going to equal x times du, because moving the dx over here and then multiplying by x to get it over there, dx is x times du. So let's try and see if our hunch was right. Integral from 2 to infinity of 1 over x times natural log of x, which is u, times dx, which is x times du. And you can see that we got exactly what we wanted. The x cancels with the x. So in the inside is integral of 1 over u, which we know is the natural log of u evaluated from 2 to infinity. But we don't want to actually do the evaluation yet because we still have our answer in terms of u and our limits in terms of x. So let's go ahead and convert that. It's natural log of u, which is natural log of x. So natural log of the natural log evaluated from 2 to infinity. And let's see what that looks like. You would have natural log of infinity minus natural log of 2. So here, natural log of infinity is infinity, and then if you take the natural log of this infinity, you're still going to get infinity. So you're going to have infinity minus a number. Whatever this number is, it doesn't matter. You have an infinite quantity minus a finite number, so the answer is infinity. So because the integral diverges, the series also diverges. The series also diverges. Okay, now the final example is going to be, what if you had the sum from n is equal to 1 on up to infinity of sine of 1 over n squared, okay? Obviously it has a sign in it. It's not going to look like a geometric series. It's not going to look like a p-series. So first thing you should try to do is go ahead and see if you can use an integral test on it. If it's integrable, then you can find out something. So that would be integral from 1 to infinity sine of 1 over x squared dx. Let's see if we can find that integral, and if we can, we might be in luck, okay? Now, I am going to take u to be 1 over x, and the reason I'm going to do that is I have a hunch that if I take u to be 1 over x, when I take the derivative, I'm going to have something that will cancel with that denominator. This all comes with practice, and that's why, you know, you see these examples and you get some experience with things to look for. You're trying to pick a u so that when you take the derivative of it, it'll cancel with something else in the integral. So if we say that u is equal to 1 over x, which is equal, by the way, to x to the negative 1, then du dx is equal to minus x to the minus 2, okay? Which, by the way, is equal to negative 1 over x squared, okay? So solving for dx, I move dx over here, and I'm going to get dx is equal to negative x squared du. Because I take the dx and move it over here, multiply by negative x squared to get dx by itself. So that's what dx is equal to. Dx is equal to negative x squared times du. Now the next thing I want to do is actually go ahead and plug that in and see what I have. 1 to infinity of sine of u, because that's what 1 over x is equal to, over x squared times negative x squared du. And that's exactly what we wanted. We got a nice cancellation between this and this. Okay, so it's going to be the integral from 1 to infinity of, I should say it's a negative, because I have a negative sign, negative integral of sine u du. Now, what is the integral of sine? You should remember it's negative cosine. So I have a negative out front times negative cosine of u, because the integral of sine is negative cosine, evaluated from 1 to infinity, but I don't want to actually evaluate the integral yet. What I want to do is I want to make this a positive, and I'm going to say it's cosine, and I'm going to plug in what I know for u, and that is 1 over x, evaluated from 1 to infinity. Okay? So then I'm going to have cosine of 1 over infinity, plugging in the infinity, minus cosine of 1 over 1, plugging in the 1. And so I'm going to have cosine of, what is 1 over infinity? It's cosine 0 minus cosine of 1. What does cosine of 0 equal? Okay, cosine of 0 is equal to 1, okay, minus, what is cosine of 1? Well, this is 1 radian, presumably. I have no idea what the cosine of 1 is equal to, but I know that I have a number minus a number. There's no infinities anywhere around there, so even though you don't know, unless you whip out your calculator, what cosine of 1 is equal to, it doesn't really matter. Because the integral converges, the series also converges. The series also converges. So in this section, we've made a great deal of headway talking about one of the first big tests that you're going to use in calculus on your test. That's called the integral test. Basically what it says is if you have a sum of an infinite number of terms, which is called an infinite series, you can sort of pretend that relation is a function, and if you take the integral of that function over 1 to infinity, which is the number of terms in the series anyway, then if that integral converges, then it means that the series converges as well, and if that integral diverges, that series diverges as well. So you're using that here, and that's what you're doing. We also looked at the p-series and trying to beat some of these things into shape to look like a p-series to find out if it converges or not. So that's a good introduction to the integral test. The trick is going to be to evaluate the integrals. You use all of your tricks in your toolbox to be able to evaluate the integrals. Once you have that, you'll know if the series converges or not.